All right, let's jump straight in. We're looking at a really exciting paper today from Sakana AI, Fast Weight Product Key Memory, or FwPKM.
And this one gets right to the heart of, a huge trade-off in large language models.
The one between storage and efficiency, right?
Exactly. You've got softmax attention, which gives you this, theoretically infinite storage, but the cost is quadratic. It just doesn't scale.
And then you have linear attention, which is super fast, but the storage is fixed. It's limited.
So FwPKM comes in and tries to give us the best of both. They take this existing idea, product key memory, and they transform it.
Right, from something static, a slow-wait module, into something dynamic, a fast-wait episodic memory.
And that transformation has some huge takeaways. First, the model can now memorize new things right from the input using these really simple local updates.
So it's like a high-fidelity episodic memory that works alongside the model's regular semantic memory.
Exactly. And that leads to massive drops in perplexity on long context data.
But the real kicker is the generalization, isn't it?
Oh, absolutely. They train these models on just 4K token sequences.
Just 4K.
And they generalized robustly all the way out to 128K tokens. They just crushed the needle in a Haystack benchmark. It's a game changer for context extension.
Okay, so let's unpack this. The paper starts by framing all sequence modeling layers, attention, FFNs, everything, as just different forms of associative memory.
Which is the right way to think about it. And
Yeah.
if you're designing the perfect associative memory, you'd want 4 key properties.
Key value association, obviously.
Right. And large storage, low computational cost. So subquadratic.
And the fourth one, the one that's always the problem.
The ability to memorize new pairs
Yeah.
at any time, dynamically.
Which brings us to the original product key memory, PKM. It was so cool because it nailed the first 3 of those.
It did, yeah, back in 2019. And
Yeah.
it did it with this really brilliant sparse access trick.
So instead of a million memory slots, you have to check one by one.
You set it up like a Cartesian grid. You only have to deal with 2 much smaller subkey matrices. So for 1,000,000 slots, that's just 2 matrices of size 1,000.
That's a huge computational saving.
It's massive. You end up with a complexity of something like ovally sorty NK. It's an incredibly efficient structure for huge sparse memory.
It was a slow-wait module.
Exactly. It acted like a normal FFN. You'd train it during pre-training, and then it was just frozen, locked in.
Couldn't learn anything new. It fails that fourth property.
And that is the exact gap that FwPKM is built to fill.
So this is where the idea of fast weights comes in, which goes way back to Hinton and Plout in the 80s.
Right. You have your slow weights, which hold all the general knowledge about the world.
And FwPKM makes the PKM's key and value matrices into these dynamic fast weight parameters that can change on the fly.
Mm-hmm.
So how do they update them? They're not running a full backprop pass in the middle of generating a sentence, are they?
No, nothing that slow. It's a local, chunk-level gradient descent. The model tries to minimize the mean squared error for a small chunk of text using the next value as the target.
And this is where that one-step rewriting detail comes in. They do something very specific with the learning rate.
They set it to exactly 1.0.
Which seems so arbitrary, but it's the whole point.
It's the whole point, because when you set the learning rate to 1, the math works out so that a single gradient step forces the predicted value to instantly become the target value.
You're not nudging it, you're just overwriting it.
You are just overwriting it. It's instantaneous memorization. It's basically test time training on this huge memory bank.
But that sounds, incredibly unstable. You're updating this giant memory bank in real time.
Oh, it is. And that's why the engineering they did to stabilize it is so important. They had to be very, very clever.
Okay, let's walk through those stabilization tricks. First step is gradient shaping.
Right. Normally, you'd average your losses over a chunk, but they found that just dilutes the signal too much.
The update is too weak.
Exactly. So instead, they sum the losses. It makes the update signal for any single memory slot really strong and undiluted. It hits hard enough to stick.
And then there's a consensus mechanism. What happens if, 5 different tokens all try to write to the same memory slot at once?
You get a traffic jam.
Okay.
So what they do is they scale the gradient for that slot by 1 over the number of times it was accessed.
So it averages out the competing writes instead of just letting the first one dominate.
Precisely. It's a balancing act. It makes the writes collaborative instead of competitive.
And they also use gating. The model gets to decide if something is even important enough to write to memory.
Yeah, a little scalar value weights the loss, so the model itself can say, you know what, this chunk of text is just boilerplate. I'm not going to waste the memory write on it.
One really surprising detail, though. They don't use gradient clipping. Isn't that super risky?
It is, but they argue it's necessary, because the target values coming from the attention layer are, in theory, unbounded. If you clip the gradients, you might prevent the memory from ever actually matching the true scale of the data it's trying to store, so they let it scale freely.
Okay, so that handles the writing. But what about reading? They talk about this problem of memory collapsing.
Yeah, that's a classic issue with sparse systems. The model gets lazy and just learns to use the same few memory slots over and over again.
So how do you force it to use the whole million slot bank?
With an auxiliary loss. They call it marginal entropy loss. Basically, when they update the key matrices, they add a reward for using the memory slots more uniformly across a whole chunk.
So it encourages the keys to spread out and cover more ground?
Exactly. It makes the whole key space available and useful.
And the final piece of the puzzle, they swapped out the dot product similarity score.
For an inverse distance weight score, which is based on Euclidean distance,
Why that change?
they found it encourages the keys to become like prototypes
Yeah.
or centroids for clusters of similar queries. It just led to better, more structured memory usage.
So a lot of careful engineering just to make this whole dynamic process work.
A ton. But the results really speak for themselves.
Let's get to those. They trained on about 5 billion tokens. But the key thing is they only used short 4K token sequences for all of the training.
And finding number one is this beautiful confirmation of their whole idea. The fast weight module, the FwPKM,
The new part.
the new part. It's the one that massively reduces perplexity on long context datasets. It is, without a doubt, acting as the episodic memory.
And the standard slow weight PKM.
That one gives the biggest gains on the knowledge-heavy, short context stuff, like Wikipedia articles. That's the semantic memory.
So they're complementary. You really want both.
You absolutely want both. They're doing different jobs, but they immediately ran into a problem with the rest of the model's architecture.
The competition with full attention.
Right. If the model had unrestricted full attention, it just ignored FwPKM completely.
How can they tell?
The gating values, they were all clustered right around 0. The model just wasn't bothering to write anything to its new episodic memory. Why would it? Full attention is powerful.
So they had to kind of force its hand.
They did. They used a probabilistic sliding window attention during training. Basically, they hobbled the full attention just enough.
And once the model realized it couldn't always rely on attention for long-range stuff.
The gating values shot up. It started using the FwPKM module heavily. It's a great example of the dynamics between different memory systems in a model.
Okay, and this is where it gets really impressive. The needle in a haystack evaluation.
This is the acid test for long context memory. They stick 5 little facts or needles into these huge contexts, up to 128K tokens, and see if the model can find them.
And this leads to finding 4, iterative memorization.
This is so cool. On the first pass, a single read-through of the context, the FwPKM models were, honestly, not great. Sometimes less than 10% accuracy.
But then you just let it read the context a second time.
Just one more time. And the accuracy suddenly jumps to over 70% in many cases.
Wow.
It's proof that it's using that second pass to consolidate the memory. It's doing test time training. Standard attention can't do that. It gets one shot.
And that ability leads directly to the headline result. 128K generalization.
From 4K training. The FwPKM models just kept on working, all the way out to 128K tokens. Their retrieval accuracy stayed robust.
While the standard full attention baselines just fall apart when they see contexts that long.
They completely fall apart. This shows the mechanism for memory is what generalizes, not just the content length it was trained on.
But, that memory isn't infinite. There's a cost to storing more information, right?
For sure. And they saw that as the context gets longer, going from 4K to 128K, the accuracy of that two-pass system starts to drop a bit.
It's getting overwhelmed.
A little bit. But the good news is you can close that gap just by running more iterations. A third or fourth pass brings the accuracy right back up. You just need more time to etch all those facts into memory.
And because it's an explicit memory module, you can actually look inside and see what it's doing.
Which is a huge advantage for interpretability. They had this case study where they could literally trace the information flow.
What'd they find?
They saw the model pull information from 16 different memory slots across 2 different FwPKM layers to correctly assemble a 6-digit number it needed to retrieve. It's robust, distributed storage.
And their error analysis was also really insightful.
Yeah, the errors weren't from the memory failing to store the information. The errors came from imperfect key matching. It would find the right token, but in a slightly wrong prefix context.
So the problem's addressing, not storage.
Exactly. It's a key space problem.
The gating case study was also fascinating, looking at how it behaved on the Sakana AI Wikipedia article.
You see this clear specialization between layers. The lower layers are just on all the time. High gating values for everything. It's like a general short-term buffer.
But the higher layers?
The higher layers are pure nullity detectors. They only fire, the gates only open for rare, specific named entities. Things like David Ha, Lion Jones, Renito.
So it's using the fast weights to capture new information, stuff the slow weights don't already know.
That's the proof. It's processing novelty.
All right, let's talk about the practical side, the cost.
Right. So in terms of theoretical FLOPs, it's actually less intensive than a standard dense MLP layer, even though it has way more parameters.
So on paper, it's cheaper. But what about in practice? Is it actually fast?
Well, that's the current bottleneck. The implementation efficiency, the actual FLOPS per second you can get, is still lower than a super optimized kernel like flash attention.
So the idea is fast, but the code isn't there yet.
The custom sparse update kernels just aren't as mature as the ones for dense attention, and they say that themselves in the paper.
That makes sense. It's a major engineering challenge.
It's the key bit of future work, really. To make this widely adopted, those kernels need to get a lot faster.
So to sum up, FwPKM is just a brilliant piece of architectural work. They've unified sparse, massive storage with these rapid online updates.
And they've shown a path to generalizing from short training sequences to enormous contexts, which is one of the biggest problems in AI right now.
It really feels like a major step forward.
I think so. And if you think about the future, the paper mentions ideas like nested learning, where you have multiple fast weight layers that update at different speeds. FwPKM gives you this huge dynamic memory bank. So what happens when you start designing a truly tiered memory system? Imagine combining different sized FwPKMs that update at different frequencies. One for every token, one for every paragraph, one for the whole document. That combination, sparse, massive, and dynamically optimized at different tiers, that really feels like the next frontier for building an AI that can truly learn in context.